Good afternoon, everyone. Today we're going to continue our discussion on two-way ANOVA and moving a little bit beyond the randomized complete block design. So remember, in the randomized complete block design, we had two factors, one which we were interested in, the other one we needed to take care of. It was thought of as a nuisance variable in some sense. And a main point in that was that we had one observation per cell in our data table. Here, in this two-way ANOVA, we still have two-factor experiments or two-way designs, but it also allows for us to be able to look at an interaction between the levels of our two categorical factors. So some of the advantages is that it's more efficient. In particular, one two-way ANOVA is generally more efficient than doing two one-way ANOVAs, basically because we can look at that interaction and we don't need as large of a sample size if your data is collected separately, rather than doing a separate analysis for each factor that we're interested in. The other advantage is that we get a further reduction in residual variation, certainly compared to doing a randomized complete block design, because some of that variation can be explained by that interaction. And so by having the ANOVA model, the full two-way ANOVA model, we can look at both main effects and at interactions. So there's our main effects and our interactions between the factors and what those effects are on our response variable of interest. So in general, we assume that we have independent, simple random samples taken from each population. So remember, if there are two factors, and if they each had two levels, that corresponds to 4 different populations. So a couple of points to be made here is that we can have more than one observation per factor level combination. Okay, so if we think about the data table, and at least the sample sizes, just to sort of set us, we'll see some of this notation introduced again later on. But we have factor A, factor B, and factor A might go from 1, 2, all the way down to I levels. Factor B will have 1, 2, all the way up to J levels. And then we can look at the totals. So inside, we would have N11, N12, up to N1J, N21, all the way down to NI1. And then that's N, capital I, capital J observations in total. And then the grand sum of all of these observations we would call capital N. So what we had seen in the randomized complete design was that these NIJs inside here were all equal to 1. We only had one observation. Going one step further than that, suppose we had I guess the way we'd set up the table was we had our treatment and our blocks, and you could imagine that you have a fully replicated one where instead of just having one observation, you still might have the equal amount of observation. So that's what's called a balanced design. So sometimes Nij is equal to little n, a constant. Okay? So it might be, and the way that the data is collected might be that for one of the factors, like maybe for factor B, we know that we're always going to have some set number of observations, and it's an equal number of observations per level of our factor A, or of the if you're looking at, say, a randomized complete block design, but with replication. That's another way to think about it. And other situations, you could imagine, we'll look at one in a moment, where there are many, many observations. So you collect a simple random sample of observations, and you don't know where in the data table they fall. So after you recruit that observation, then you look at what are the values of factor in A and factor B that they have. And so they might be different sample sizes in this table. Okay, so let's look at a couple of examples that are in your textbook, just to sort of look at the differences between these and how we think about these interactions. So this is example 13.5 from your textbook. It's on sugar-sweetened beverage consumption, or SSB for short. And previous research has already suggested that the sugar-sweetened beverages are linked to type 2 diabetes as well as obesity. So this survey is called an NHANES survey. It's a National Health and Nutrition Examination survey, where the goal was to estimate the consumption of sugar-sweetened beverage consumption among children. So they're not focusing on adults, it's just on children. And they had over 14,000 participants. So they recruited these children, divided them into these 3 age categories. So here's an example where it's observational. We just need to, we can't change a child's age. We just observe what the age is, and then they were binned into these 3 groups, either preschoolers, pre-adolescents, or adolescents. And this data had been collected over 2 different time periods. So there's from 2003 to 2006, and participants from 2007 to 2010. So what we have in our data table is our response being the average, or the sample mean, sugar-sweetened beverage caloric intake among these children, where now they've been more or less stratified by whether they were preschoolers or pre-adolescents or adolescents, so by age group and by year. Are these averages for 2006 or for 2010? So just to kind of make a comment here, this table doesn't tell us about sample sizes. So we know what these averages are and what the group means are. So for instance, we can see that the consumption in 2010 was less than that in 2006. They might have chosen these 2 years because this is before some campaign was out that sort of suggested not taking sugar-sweetened beverages, and maybe this one was after that campaign or that time point. And then looking at the age, we can see that the group means they're increasing by age, but we can also look at what are the trends within each year, this profile. And so this was what our grand mean is here. So what are some questions of interest we might have? Well, to start, we might think, what is the marginal mean for 2006? Well, the marginal mean, remember, that means we want to look on the year margin, and we will more or less ignore or wash away information about the preschoolers. So that's this 242 right here. What is the marginal mean for sugar-sweetened beverage consumption or caloric intake for adolescents? Again, here is one where we want to look at, this is for year, and this is for age group. So that's the year margin, and this is the age group margin. So the age group margin is here, and we see for adolescents, it's 318. But there are more questions that we might be interested in, is that we're not interested in a particular margin, but we'd like to know, is there an age effect or a year effect? Age makes sense. As you get older, you could imagine they might drink more. So even if they're drinking the same beverage, because they're drinking more of it, there might be a higher intake, right? Particularly among children. So we might be interested, though, is there an age effect? If there is, we wouldn't be surprised. Is there an age effect of year on the caloric intake? So in terms of the age effect, you might see it go the other way, depending on your data, that as the children get older, they're more educated about making healthy choices, and you may see there's a decrease in that caloric intake. That might be another hypothetical situation. But you might be just interested in, is there an age effect? Is there a year effect? Is there an interaction between age and year? So as someone gets older, or if you look at what's the effect of age for a given year, does it change when the year changes? Does that affect? And vice versa. Okay, so if you compare participants of a certain age in 2006 to 2010, is that difference differ when you look at a different age group and compare 2006 to 2010. So a useful plot to look at is the one shown here, where we have our age group along the bottom, calories per day in the top, and then what we're plotting are just the averages, right? So we had 170 for the 2006 group, right? So if I plot this across, that's about 170, and for this group, it's 130. So technically, this is taken right out of your textbook, but I think it's better to say average or mean calories per day. That's being more precise. So what we can see is that this is called an interaction plot because we've got a different profile across the age groups for each year. And what we can see is pictorially the caloric intake increases for older children, but we also see the key is that these lines don't cross. Okay, so with that, it's suggestive that perhaps these profiles are roughly parallel, which would be indicative of not having an interaction. If there was an interaction, then we would expect to see lines that are not parallel, and they might actually cross in the image, or when we look at the figure and we think about extending the lines, it might look like they would cross at some point. So this is basically giving us guidelines on how to interpret our plots. And going back to the plot that we've got at hand, what we can see is that the 2006 profile is not exactly parallel to 2010, but is close. So here we see a little dip and then it goes back out. So to see if that's a genuine difference between them is something that we'd probably want to use two-way ANOVA to look into. And then from the inference sign, when we do the ANOVA, it helps us to address, are the observed differences due to chance variation, or could it be due to a main effect or interaction of these factors? Okay, so let's look at another example. This is example 13.6 in your textbook, and it's on asking the question, do people tend to eat more when they eat in groups? There are a couple of possible mechanisms that had been thought through. So one is being that you eat more when you spend more time eating, and then if you're with other people through conversation and such, maybe you spend more time uh, sitting around the table to finish the meal. So, in fact, Health Canada recently, if you look at a lot of their documentation that they're sending out, they will say, sit and have a meal with friends or sit and eat with your family. This is part of the reason is they want you to spend more time sitting and eating. There, it's not necessarily so that you eat more. It's also so that you have, I believe, more time for your food to digest, or that you digest your food better. But the point is that there is some interest in what happens when you actually eat more, or what happens with eating in groups. Because if you eat more and you are somebody who's already at risk of diabetes or obesity or have them, then maybe this is also something to think about. So in this particular study, the response was the time in minutes spent eating lunch. So they only focused on one meal, lunch, not dinner. And there were two factors of interest: the number of people eating and the setting in which you were eating. So the idea being that if you're sitting at your workplace, maybe you're not as rushed to get out of the restaurant or to get back to work or what have you. So they contrasted that with fast food restaurant eating. So there might be one or a group of you who go to a fast food restaurant during work hours, or for as lunch for lunchtime when you're at work. So here's what our data looks like. And again, looking at the numbers briefly, we can see this one is giving us the number of people eating. So this is the marginal mean for number people, and you can see it tends to increase. Marginal means for setting is what we have down here, and what we can see is that workplace mean is higher. Okay, so the eating times tend to increase with the number of people, and the workplace eating times tend to be longer. These are the average eating times, tend to be longer than the fast food restaurant times. So what would the interaction plot look like for these data? So that is given in the figure on the next page. I can pull up this sheet. And there is the plot. What can we see? So it looks very different from the previous example with the adolescents and the sugar drinks. In particular, we can see that this gap between our two curves are changing. So gap between profiles getting larger with increase in number of people eating. So remember I'd said before, what we want to look for in these plots is one of the things is there presence of an interaction? Clearly, these lines are not parallel, so there is evidence of an interaction. And you can see, well, we can't go less than one person eating, but you can see that if this line was to continue, these two profiles, they would eventually cross. Okay, so whenever we interpret our results, we need to keep that in mind. What else? The increase in the meal duration. There's an increase in meal duration as the group size increases, and that increase is greater in the workplace setting compared to the fast food restaurant setting. So that's another way of talking about that gap. So the gap between the profiles gets bigger as group size increases. It's probably a nicer way to word it than I did up above. And because of we see this difference in the group, so the effect of group size on eating time depends on the setting, or the group of the setting on meal times depends on how many people are eating. Because of those differences, we need to account for that. That's actually what we mean by an interaction and needs to be accounted for in our ANOVA table. Okay, so let's start looking at our inference for this two-way ANOVA. We have two factors, factor A with I levels, capital I levels, factor B with capital J levels, and the numbers inside, if we think about the sample size, there are Nij from each of these A times J normal populations. So the populations associated with each one of them is a mean, mu ij, but we assume a constant standard deviation sigma. So this is your common standard deviation across all of the groups. So that means, when we come to estimate this, we're going to have to use some type of pooled estimate of standard deviation. Each observation, xijk, can be written in this way. These should be subscripts, so it's mu sub ij plus epsilon ijk. So each individual has its own error, but the mean depends on what level of factor A and what level of factor B that the observation falls or is taken from. So I goes from 1 to capital I, J is 1 to capital J, and K is from 1 to Nij. So it's up to the number of observations in that factor level combination. These epsilons are considered to be a simple random sample from normal populations. And again, that's where we're seeing that constant standard deviation sigma and then mean 0. So in general, you want to make sure that be comfortable with assuming a normal normal distribution for each of these populations. That's for the response in that combination of factor levels, and that they have a constant variance. So those are two different things that you could look at through an exploratory analysis. The population parameters, now we have capital I times capital J of them, because there are capital I times capital J normal populations that we are interested in or assuming. And then they all have, so this is how they would fall sort of in our table, and then they all have this constant sigma associated with them as well. Okay, so we understand what our populations look like. We understand that within each one of these populations, remember I used to always draw a little circle or a bubble for each of the populations and then drawing a random sample, but now we have capital I times capital J of those. And so this is the mean in the population and the standard deviation at the population level. Once we collect our random samples from each of these populations, we estimate the parameters with their sample counterparts. So we estimate mu j with x bar ij. To estimate our sigma, what we want to do is estimate it with our pooled estimate of variance. So what that means is for each one of our, that squared should be up here. So for each one of those cells, in this table, remember we're considering all of the observations in the 1, 1 cell coming from the population with factor level A equal 1, factor level B equaling 1. Okay, that the level is the first level of both. So when we collect our data, we would have X bar 1, 1 all the way up to X bar IJ, and we'd also have S11 all the way up to SIJ. So for each one of these populations or random samples, we can calculate the sample mean, the sample standard deviation. So the sample standard deviation is the sum of the squared difference between the observation and the cell sample mean divided by the sample size minus 1. So here, and then taking the square root. So SP squared is going to say if I know what those sample standard deviations are, I can square them to get the variance. I can multiply by Nij minus 1. So I essentially have the sum of the squared differences of each observation from its cell sample mean. And then I'm going to divide by the sum of this double sum Nij minus 1. Okay, so that's essentially going to give me all of, if I sum these all up, I'll have capital N, like summing up all of the Nijs, looking back at what we wrote on our first page today. If I summed up all the Nijs, I get this capital N. And then I have 1, which is a constant, so that's going to give me, and I'm going to have capital I times capital J of those. So we could actually write this as the sum Nij minus 1 Sij squared all over capital N minus Ij. So the analysis of variance for two-way ANOVA is very similar to what we did for one-way ANOVA and for the randomized complete block designs, except now our sum of squares model, remember for the randomized complete block designs, we looked at the sum of squares model and we broke it up into these 2 bits, sum of squares for our treatment plus sum of squares for the blocks. So we'll play a similar game here. We look at our sum of squares total, decomposes into the sum of the sum of squares model plus sum of squares error, as does our degrees of freedom decompose into those 2 bits. We can calculate our sum of squares total and the sum of squares model, but both the sum of squares model and degrees of freedom model can be further partitioned into the main effects and interaction. So let's take a look at what those main effects and that interaction term look like. If we partition the sum of squares model and the degrees of freedom model by our main effect of A, the main effect of B, and an interaction term, then we can interpret sum of squares A as being the variation among the means at different levels of factor A. And remember, A has those capital I levels. Similarly, SSB can be the variation among the means at different levels of factor B, where B has capital J levels. So, what about the degrees of freedom? The degrees of freedom for A is equal to I minus 1. Degrees of freedom due to factor B has J minus 1 degrees of freedom. And this is analogous to when we had one-way ANOVA with I levels of our group variable. Then we had I minus 1 degrees of freedom. And in randomized complete block designs, when we had the blocks, we had B minus 1 degrees of freedom when there were capital B blocks, but factor B has capital J levels, so we have J minus 1 degrees of freedom for factor B. And then the degrees of freedom for A and B are I minus 1 times J minus 1. This is kind of like what your error was in the randomized complete block design, because remember there we didn't have an interaction. So this is what the degrees of freedom turn out to be. And now we can rewrite our sum of squares model into the sum of squares for A plus sum of squares for B plus sum of squares for AB, and do the same thing for our degrees of freedom model as well, because remember we wrote these all out or defined them on the previous page. So our sum of squares total now has, instead of SSM, we can have the sum of squares for A plus B plus AB plus that error term. And the sum of squares total is also, the degrees of freedom total is also degrees of freedom for factor A plus that of B plus the interaction plus the error. So in general, the calculations get pretty cumbersome, and so often software is used to calculate what all those different sums of squares are. But there is one special case that is easier to think about, and that's the special case I mentioned earlier. We have something that's like a balanced design, and that Nij, so the sample size in each cell is equal to the same, is the same sample size, is equal to n for all ij. When we do this and we look back at our formulas for sum of squares model and sum of squares A and B, this means we can actually replace the Nij that we had in sum of squares model by n. So we had before double sum Nij times x bar ij minus x bar squared. But we can write this, replace it by n. And now we can see that this n can be brought outside. Okay? And we can actually play the same game for looking at the sum of squares for A and the sum of squares for B. So we would have had this double sum here for I and J, and there would have been an Nij in there, but we replace it by n. Well, actually, we would have had, the total sample size for J, and it turns out that we'll have capital N times capital J of these terms. So we have our sum of squares. It'll end up being, I didn't write it out in full this way because we would have to introduce a little bit more notation, and there's no need for it. So the point is that we would have had a double sum, and when we replace remember there's no J, so this term is the same for all J, and when we look at the sample size in each cell, we can replace it by n, so we end up getting this Nj, capital J out front. Here, when we actually write this as a double sum over I and J, the Nij's become N's. This term right here does not include an I. So when we look at it for every term of every value of little I, we end up getting capital I of those. So we have capital N times capital I times the square difference between each of the factor B means and the overall mean. Okay, so these two are factor level means minus overall mean. Okay, and this one up here, we just have the observed mean minus the overall mean. And if we have the sum of squares model, this is usually easier to compute than looking at the formula for the interactions. So we can calculate the sum of squares for interaction by subtraction. So that gives us all of the pieces well, almost all of the pieces in here. We also already know how to compute the sum of squares total. So with that, we know how to calculate the sum of squares error. So here's what our ANOVA table actually looks like. Now our source has, remember in the randomized complete block design, we had our treatment, which is akin to factor A, our blocks, which are now actually factor B, because it may not be a nuisance. It may be something we're actually interested in. But we have our degrees of freedom as being I minus 1, capital J minus 1, the product of capital I minus 1 and capital J minus 1. And then total is still capital N minus 1. Remember, the sums of squares is looking at the observations minus the actually, let's go back here. These ones are the observed cell means. That's what I should say. And so we have our capital N minus 1. Sums of square total is always the observed minus the overall. And we have all of these. So we can compute the, we can compute the error term by looking at the difference between the sum of squares total and these other sums of squares. We can also calculate the error sum of squares as a difference between the total and this A, B, and A, B and their interaction. So this, actually, even if you think about it, the sum of squares error, remember our mean square error is essentially our pooled estimate of variance. And remember, we talked about how the denominator, when we calculate S sub P, actually simplifies to being capital N minus capital I times capital J. So that is what our degrees of freedom is for the error. And we put these two together. So this is our mean square error, which equals SP squared. So the mean square, same game as we had before. It's looking at the ratio of sums of squares over degrees of freedom for factor A, sums of squares over degrees of freedom for factor B, sums of squares over degrees of freedom for the interaction. And then the F is looking at statistic, the mean square for each factor divided by the mean square error. So we have MSA over MSE. So this one we might call F sub A, F sub B, F sub AB. And as usual, once we have our ANOVA table, we can take the square root of our MSE, and that's our estimate of the pooled standard deviation. Okay, so there are a few different tests that we can do with these two-way ANOVA tables. Remember, we said there we could test for main effects and interactions. Usually the first test we do is looking for the interactions. So the null hypothesis is that there's no interaction between factors A and B against the alternative that there is an interaction between those two factors. We use our F sub AB to be our test statistic. So this is one where we have our F distribution, that's the value of our statistic, and the upper tail area is our p-value. This F distribution has degrees of freedom inherited from the numerator and denominator mean squares. So if we look back up for factor A, we have degrees of freedom being capital I minus 1 times capital J minus 1, and the error is N minus IJ. So those are the numerator and denominator. So this is numerator, degrees of freedom, denominator, degrees of freedom. And the upper tail area is our p-value. If there is not a significant interaction, then we're probably more interested in focusing on what those main effects are. If there is an interaction, then we would want to look further into understanding the nature of that interaction. So if we are looking at the main effects, there are two different ones we can do. So there's looking at the null hypothesis of no main effect of factor A versus the alternative that there is a main effect. Again, you can think of this as a two-way, a two-sided, somewhat associated with the two-sided test. And here we have that our F sub A, because we're doing the test statistic for A, is the ratio of the mean squares. The degrees of freedom change, so the denominator still has the mean square error, so we have n minus ij degrees of freedom in the denominator, but the numerator now has mean square due to factor A, which has I minus 1 degrees of freedom. And then the p-value is the upper tail area for that statistic. So that's our F sub A, and there's our p-value. For factor B, it's the exact same story. We have the main effect of factor B is the no main effect of factor B for the null hypothesis. The presence of a main effect for factor B. Our F statistic is the ratio of the two mean squares, but mean square B has J minus 1 degrees of freedom associated with it, so that's our numerator degrees of freedom. Mean square error is capital N minus NJ, so that is what our degrees of freedom are here, and then the p-value is the upper tail area here, F sub B, and that's the p-value. And this is where we'll have to use that table E. So if we find there's evidence to reject any of these null hypotheses, then we're into the realm of doing contrasts and multiple comparisons in order to identify what the nature of these effects are and be able to quantify how large these are. Oh, there's a typo there. So next class, that's what we'll do, is we'll continue this discussion on two-way ANOVA. Okay, bye. See you next time.